Okay, you've probably noticed in lab that sometimes we carry out an experiment, and if you have perfect data, you can see the relationship you're looking for, like, oh, I doubled this concentration and the rate doubled. But you probably noticed, especially with that Hess's Law lab, that sometimes data can be messy, and it's better if you evaluate a huge amount of data instead of just looking at 2 points. When I made this change, what happened? So it's better to make several changes and say, on average, what happened. The integrated rate laws allow chemists to do this. So if you use calculus, you can take the integral of either a first order rate law, that rate equals k times concentration raised to a power, or take the integral of a second order or the third order, or the zero order, and you'll get these different integrated rate laws. These are given to you in your Gregor sheet, you know, the sheet that you get with every test for AP Chemistry. So you don't have to memorize them. You'll never actually have to use calculus in AP Chem. Don't have to. But what it does allow us to do is, by having these rate laws, we can actually plot a graph, and graphing data allows us to see, are we following this pattern or this pattern? Do I have a first order, a second order, or a zero order? So really what we're doing is we create graphs in order to see which graph produces a straight line. So if I graph the natural log of a concentration versus time, and it gives me a straight line, it's first order. If 1 over the concentration versus time gives me a straight line, it's second order. And if concentration versus time gives me a straight line, it's zero order. And the reason this is, so what the chemists are doing is they're going into a lab, and they're changing their concentration, and then they're saying, like, they're actually measuring, like, how much concentration do I have over time? So they'll carry out the lab and measure many, many points, and they'll say, well, how, you know, as time changes, what's the concentration going to be? So they're collecting, as the reaction occurs, the different time points and the different y points. So it's like the time is going to be your x value, and the concentration that you have at that time is your y. Because the concentration of reactant that you have depends on how much time has gone by. Okay? So if it makes a straight line, what we're looking for is y equals mx plus b, right? A linear equation. Y equals mx plus b. So we just said concentration is going to be the thing that changes depending on time. So natural log of a at time t. So that a is going to be my y, right? It changes based on time. This t is going to be my x. And this guy right here, this is natural log of the initial concentration. That 0 means at time 0. This t means at whatever time. So this guy is going to never change. Like, this is just 1 point. This is my y-intercept. So this is my b. I want to rearrange this to make a straight line. So what I'm going to do is I'm going to add natural log of the concentration of A initially to both sides. And this cancels out. And I'm left with the linear equation that I get is the natural log of the concentration of the reactant at some time t, whatever time it is equal to negative k. So that's kind of the factor that's relating how fast concentration changes times how much time has gone by, plus the natural log of your initial concentration. So what that means is y, right here, equals mx plus b. So if I plotted this, if I went into lab and I collected concentrations depending on different times, and then I took a natural log of those concentrations, and I plotted the natural log of the concentration versus time, if it is a first order reaction, I should expect a straight line. And I'll have a straight line where the slope, that's m, the slope of this line is equal to negative k right there, negative k. This intercept, well, y equals mx plus b. My intercept is natural log of the initial concentration right there. Okay, so basically, if it's a first order reaction and I plot the natural log of the concentration versus time, I get a straight line. So what chemists will do, they'll collect their data, they'll plot. If it's a straight line, they're like, success, I got a first order reaction, we know this is a first order. If it's not a straight line, if it looks something like any other kind of line, they know it's not first order. Okay, so then they say, well, how about second order? We have this integrated rate law for second order. I need to rearrange this so it's in the y equals mx plus b. Here's my concentration at whatever time, so this is my y. Here's my time, so this is my x. This must be my b. I'm going to add 1 over the initial concentration, which doesn't vary, so it makes sense that it's my intercept, because this doesn't vary. So plus 1 over concentration of A, initially. That 0 means time 0, so initially. So I end up with 1 over your concentration at whatever time, because that does change, that's a y, equals K times time plus 1 over my initial concentration, A at time 0. Okay, so here's my y equals mx plus b. Alright, so I am a chemist, and I carried out a reaction a bunch of times, and I got to figure out what the concentration was at all the different times throughout, and I went ahead and plotted to see, like, is this a second order reaction? So I plotted 1 over concentration versus time. And if it's a second order, I can expect a straight line, and I can expect to have the slope is equal to k, right? Let's see. And actually, oops, I did this backwards because my slope is in negative k here. So, oops, and it's positive k. My bad, sorry. So I should have that guy. Negative slope because it says negative k. And this guy is going to be positive slope. Oops, okay, again, so slope is going to be equal to k. Here the slope was equal to negative k. And, okay, so if I get this straight line from plotting 1 over the concentrations versus time, I have a second order. For this guy, I'm just going to have concentration equals kt, the rate constant times the time, plus the initial. This is my y equals mx plus b. Okay, so in this one I should be able to plot y versus x, concentration versus time. And I know the concentration is changing, it's going down as time goes by. So if I just plot concentration versus time, it means I have a 0 order, because that concentration decreased at a steady rate. Okay. So the main point is that chemists will collect the data of concentration versus time, and then they'll say, okay, we got to figure out, is this a first order, a second order, or a 0 order reaction? And they'll try each of these plotting formats, and whichever one provides a straight line, only one of them will give them a straight line for every reaction. That'll tell them, like, ha, straight line when we have concentration versus time, this is a 0 order reaction. Okay. Or 1 over concentration versus time gives me a straight line, ha, this is a second order. Okay.